I thank the Plan 9 Foundation for the opportunity to talk about one of my goofier projects called Amber. And Amber came to be through my studies of the Plan 9 literature, where I somewhat inevitably came across Mr. Rob Pike's paper describing the Windows system 8.5 in 91. And as a short reminder, 8.5 is the predecessor to Rio, which is the predecessor to Nile, which Mr. Anthony Soros talked about yesterday. And I will bring up the family tree Amber sees itself in again later. When I read the 8.5 paper for the first time in April of last year, a deep feeling of awe came over me. And in my then established context, not knowing of Plan 9, only the heavily weighing behemoths, Xorg, SDL, Wayland, and maybe Quartz and DirectX and N-curses, made up my understanding of what computer graphics windows are. I felt as a lone archaeologist uncovering the remnants of a lost civilization still faintly gleaming of long-lost power. And it is this fascination with the 34-year-old technology I hope to in parts share in the following quarter of an hour. Alas, 8.5 is wholly inaccessible. 8.5's bedrock is Plan 9's kernel feature of constructing per-process file system views with /def/bitblit and the other devices' meanings varying based on who writes or reads from them. I know of no other way than intrusive kernel modifications to recreate this environment on modern Unix. Not even Fuse, which can emulate some of the custom file servers present in Plan 9, to my knowledge, tells the virtual file who opened it. And to fully switch to Plan 9 for my daily driver is not an option, as I don't own a 3-button mouse. Yet it turns out that 8.5's use of the file system namespace as a communication primitive isn't integral to its concurrency and self-similarities. As both of these properties were already present 2 years prior, implemented without the Plan 9 kernel. And it is this very paper, A Concurrent Windows System, Amber is an artistic study of. Before going into detail about window managing, I want to talk about one promise communicating sequential processes holds for the human-machine interaction setting. CSP is all about various agents, the sequential processes trotting along at their own pace sequentially, and then at points they understand communicating with one another before falling back to their sequential routine. As explored in 85 in the Squeak, a language for communicating with mice paper, statically unrolling the combinatorial explosion generated from these interactions is a non-trivial compilation step for Squeak. And when this unrolling is done manually, as is the case when writing for a traditional event stream-based system, failure to precisely cover the semantics of each case leads to buggy behavior. The promise, then, is that by using a runtime scheduler to implement CSP, the combinatorial explosion is contained and encoded into the dynamic state space of the running executable with precise semantics lexically defined in the CSP language being followed to a T. And while I struggle with the myriad of hiccups present graphical user interfaces present themselves with to me, most infuriating to me personally on a daily basis are the inconsistencies, graphical bugs, and periods of unresponsiveness on my TTY as exhibited by the editor Vim. I won't berate Vim any longer, as after the passing of Bram Molinar, I'm much more inclined to praise Vim for being one of the very few keeping the VI way of thought alive for over 30 years. Having now connected the CSP promise with the TTY, I can finally state what Amber is about. Such Amber is an implementation of a concurrent self-similar Windows system inspired by the ideas presently discussed, driving the TTY as flavored by Extern. To summarize, I have put together an excerpt of Amber's family tree spanning over 40 years from the original CSP paper in '78 to 2024. This arrow from CSP to Plan 9's rendezvous system call is an artistic liberty of mine, but I put it there to emphasize the secret sauce in 8.5 as the semantics of read and write system calls blocking are synchronization primitives analogous to CSP channel operations. And precision in concurrency semantics is vital for the system. Even a little slack is seen in some network file systems. Showing such slack isn't a deal breaker for traditional file systems, undermines the design of the entire Windows system. Along the top line, you can see the evolution of how CSP went through the various languages to land in a concurrent Windows system. And this eventually led to 8.5. 8.5 then gave Rio, which then inspired Nile. But the CSP lineage went further through the decades, through the various languages, and then with other influences fused in 2009 into Go, and I wrote Amber in Go. So the '89 paper, Concurrent Windows System, together with Go, then gave rise to Amber in 2024. So what makes up a concurrent Windows system? This is from the original paper. You have a client, and this client knows about itself and has a precisely defined interface with the world. In this case, some graphical window capability and then keyboard and mouse input. For Amber, this interface looks like this. So I have a capability to get the dimensions I need to draw myself in. I have a capability to push a char map out, and I have a capability to get keystrokes in. And then there's also a suspend capability, or there's also a terminate capability, and crucially on the TTY you can press Ctrl-Z, so you have a suspend capability. There are certain special properties of the TTY as compared with traditional GUI environments. And these, for one, are that the entropy in each frame is small enough that you can actually shove it fully through a channel. And because the TTY is based on standard file descriptors, there is no master clock for some FPS. There's no master clock, so you can leave the entire concurrency of the system fully to the scheduler and get updates events as they come. And one property I like in particular is the modeling of the suspension capability, in which I used a triple channel, which only is possible in languages which have non-statically named channels, such as Go. And this was something which, in my understanding of the language family, became possible in the limbo area, in the limbo times, where you have some global garbage collector which takes care of these channels. And so maybe at first glance the channels all point in the same direction, but the owner of the channel changes. So a client is notified it should sleep, and then it can notify back it's ready to sleep. Then the master TTY driver can actually put the OS to sleep, and when it gets the wake up signal, it can then relay the waking up through the chain. And so this makes Control C a self-similar operation. So Control C can fully propagate through the system. Okay, I have a demo. So you can see that it works. So in this demo, I have one coin process which spins a coin, and then I have a window manager which puts two windows side by side. And so you can see at the bottom, at the very bottom, this is selected. So I can select from both of these windows, and then if I am inside this window, I can select these two. And so I can change the coin's height, or I can reset them, or I can reset their angle, and it propagates fully through the system, and also resize events are fully propagated through the system. And if I put the executable to sleep, it truly sleeps in the OS sense, and then I can wake it up, and it propagates the wake up call through the managing windows and through to the individual. And I can also quit, and if I quickly look at the implementation, it is really it is really a very simple core, in the sense that you drive with a terminate capability, because the Control C key gets pushed through as a key. And so if I want to use it, I need some sense of looping termination signal. But then I manage a coin process and a managed double coin process. And these coins also turn at speeds which in seconds are reciprocal primes. And so if you had a system with a master clock, to get precisely these concurrency semantics, you would need an enormous frame rate. But because the scheduler knows of a much finer, or has a much finer time control, you can describe these very concurrently intricate systems. And as a closing thought, one thing I want to add is to use pseudo-terminals to get the other side. So I'm currently driving the TTY, but it would be nice to have the other side too, so that I can define a network protocol for the channel interface and then emulate SSH's pseudo-terminal, and then some coloring possibly. And my ultimate goal is to create an editor I like. So I want to recreate Vim, but in a somewhat more concurrent way, and so Amber will be the basis of that. Thank you.
Awesome stuff. We're not seeing any questions online. Anyone here got any questions? Please queue up at the mic.
Are you aware of charm.sh? It's a Golang library to do stuff with the terminal as well. They do have like some kind of transparency as well. Not as well done as
Jam.sh?
Charm, CHARM.
Charm.
Yeah.
Charm.sh. No.
Yeah, it's a Go library for like colors and all sorts of effects and anyway. Charm.sh is the website. All right, looks like that's it. Then thank you again very much.